Hello everyone. In this video we will continue to examine the Bohr model of the atom. Alright, so as described, we are unpacking the Bohr model of the atom, the first successful application of the wave function. And we have described the Bohr model of the atom as involving considering the electron, or the wave function corresponding to the electron, as a standing wave that is only stable at integer wavelengths around the proton. So when the electron, or when the wave function corresponding to the electron makes a standing wave at a particular radius, that corresponds to a stable state for the electron to be in. In order to move forward, though, we're going to integrate results both from classical physics and this particular quantum hypothesis. And the thing to remember is that the electron is bound to the proton by the electromagnetic force, and therefore by Coulomb's law. So we're going to mix models here a little bit in sort of a funny way. We're going to say, well, look, the forces are going to be related just as they are in classical physics. That is, the electric force is providing the total centripetal force for this electron orbiting the proton in uniform circular motion. And we're going to combine that understanding of what is going on with the understanding given by the wave function itself, which we'll see in a second. As a quick reminder, the centripetal force is the outcome of whatever the force is that is moving the object in a circle in uniform circular motion, and therefore mv squared over r is equal to k q1 q2 over r squared. The electric force is providing the centripetal force. In this case, we can plug in particular values, or substitute in particular values. The charge in both cases is the elementary charge, so this becomes e squared, and the mass becomes the mass of the electron. Okay, so this is our fundamental relationship here. But we're then going to combine it with the quantum, with our quantum understanding of what is going on, which manifests in two different ways. The first is that the wavelength obeys the de Broglie hypothesis. That is, the wavelength is related to the momentum by lambda equals h over p. The second quantum hypothesis is just the one that we've talked about just now, which is that only an integer number of wavelengths fit into the circumference, into 2 pi r. So integer here means 1, 2, 3, 4. It really means the natural numbers. So the integer number of wavelengths fit into 2 pi r to form a standing wave. And we're going to combine these two facts here, and we're going to derive that 2 pi r over n equal to the wavelength is equal to h over m times v. So we take these two quantum hypotheses and we relate the ultimate radius allowed for a given state indexed by n to h and the momentum itself. Then we rearrange a little bit. Okay, so we take mv times r and multiply by n on both sides, divide by 2 pi, and that gives us this relationship right here, which is a stop along the way, and actually an incredibly important one for the IB. This is a funny stop, though, because this equation basically says that the angular momentum of the atom itself ends up being quantized, right? The allowable velocities, or more accurately, the allowable combination of mass, velocity, and radius, known as the angular momentum, is quantized and indexed to n. So the only permissible values of this are h over 2 pi, 2h over 2 pi, 3h over 2 pi, so on and so forth. Now, in the IB syllabus, this is a little bit strange because we've never formally introduced angular momentum, and in fact, I don't want to get bogged down in it. It can be a challenging concept on its own. Angular momentum is formally defined as the radius cross the linear momentum, so r cross p for those of you who have cross products. But in practice, what this means is just the sort of spinning momentum, is a way to think about it, can only come in particular values. And as a result, this combination of m, v, and r can only come in particular values, which is a fact we're going to use moving forward. You should know where this equation comes from, and you should be able to apply it in particular circumstances. The IB will ask you questions that directly apply this particular relationship, and you should be comfortable identifying it as the quantization of the angular momentum. Then, once you have this, we are then going to rearrange it and solve for the velocity. Capturing the fact that the velocity can really only be particular values in order to be in accordance with our quantum hypotheses, the de Broglie hypothesis and this application of the wave function here. We arrange and solve for v, and then we insert it back into our classical force relationship, right? So here we're sort of melding the two models and seeing where it takes us. So we go ahead and do that. That gives us this nasty expression here, and happy to allow you to work out the algebra for yourselves, but once we have this expression, we can solve for Rn. I've relabeled R as Rn because at this point, once we've added the quantization of angular momentum, the only allowable radii are the radii that satisfy this relationship, which means the only allowable radii if we solve for Rn, will be the radii for which n is 1, 2, 3, 4, etc. So we solve for Rn in this relationship, and that gives us this, which is basically n squared, times a whole mess of constants. And that suggests that for the hydrogen atom, the radii of the electron orbits are quantized. They only come in units of R0, where R0 is this mess of constants. They grow as n squared, which as it turns out is not true. So that's one of the flaws of this particular model, is that the radii don't grow quadratically with n as you get bigger. But this is one of the few flaws of this particular model. But most importantly, what's interesting about this is that this mess of constants right here, R0, that is the Bohr radius, which we've actually seen before in this course. This is the sort of ground state electron radius that's used as sort of the radius of the hydrogen atom. So when in topic 7 you were required to memorize, or at least ballpark, the radius of the atom as roughly 10 to the negative 10 meters, that's really in reference to this particular constant. And as a result, this is a pretty important result. We get that the radii of the allowed electron orbits are quantized, that this is the ground state. The exact quantization, that is the fact that Rn grows as n squared, is not quite true, but as we'll see, it can allow us to derive some relationships that do turn out to be true and verifiable.